So, before I can really get into how to relate exponential growth and decay to differential equations, we have to talk a little bit about solving differential equations that are of a form that you haven't seen yet. When we talked about slope fields back in the first section, we said, you know, as long as the differential equation is just involving x, it's not an issue. You just do the antiderivative, and then that's your solution, right? Because a differential equation essentially is just an equation that is a derivative. And so if the differential equation only has x in it, then you just take the integral of that, and then integral undoes the derivative, so there you go, you're done. But if we have some sort of equation that's involving both x and y, like, for example, maybe we got something like that, dy dx equals xy squared. And so far, all we've been able to do with something like that is to make a slope field with it, graph what the slope field looks like, and then if we have a particular point, we could put a curve through that slope field, and okay, so there's what the solution looks like, but we don't know what its equation is necessarily. Well, if we have what are called separable differential equations, we can actually come up with a solution. We can actually come up with an equation for it. Okay, and this is a type of separable differential equation. That's an A. Separable. All right, and if it's separable, you should be able to, bless you, should be able to have the formula for it be of this variety. So if you think of it as like a multiplication of two functions, one involving x and one involving y. Okay, so like an f of y, be careful there, it's not f of x, it's f of y, times g of x. So if you look at that example one that I put up there, that xy squared, do you see how that one is a separable differential equation? It is something involving x multiplied by something involving y, right? xy squared. It works. It's separable. Okay? So the way that we solve this is we want to have everything involving y on one side of the equal sign and everything involving x on the other side of the equal sign. That's why they're called separable. I'm able to separate the two of them. Okay? So in this case, or if it is of this form, then I can do dy divided by f of y equals g of x dx. Or, if you like this better, whoops, forgot my dy. So it'd have that kind of a look to it. 1 over f of y dy equals g of x dx. So I've got all the y stuff on one side, all the x stuff on the other side. And from there, you just take the integral of each side. The left side would be with respect to y. The right side would be with respect to x. It'll undo the derivative of each one piece at a time. And then we should be able to get a solution to that. Okay, so let's try this one. See if we can do it. So, if I separate this thing, I'm going to have 1 over y squared dy equals x dx. All right, so then think about doing the integral of this and the integral of that. So we're going to do two separate integral problems there for each side of it to solve this thing out. Bless you. So 1 over y squared, probably easier to think of that one as y to the negative second power. So if I was going to do the antiderivative of y to the negative 2, what would that be? So you bump the power up by 1 to make it y to the negative first. But then what else needs to be there? make it negative. Because if I were to do the derivative of y to the negative first, I'd have to do times -1. Or I'd bring down the -1, sorry. Yeah, so you'd have to have a negative there to compensate for that. So yeah, so that's the antiderivative of that, plus a constant. I'm going to call it C1, because we're going to get a constant on the other side too. What is the antiderivative of x? Nope, that's the derivative of x. Antiderivative of x. There you go. 1/2 x squared. And then plus, call it C2. There's another constant on that side. Okay, now, a constant is a constant is a constant, and a constant plus a constant is a constant, and a constant minus a constant is a constant. Right? This is an important fact. Anytime you have two constants and you add or subtract them, you still have a constant. Right? So if I do this, nobody should be upset with me. I don't know what the constants are. Yeah, it's going to be something different from what the other two were, but it's still just some constant that's going to end up over there, right? If I subtract the C1 to the other side, so I'll just call it plus C. So in practice, when you're doing these, you really only need to put a plus C on one side and ignore the other, because you could always just subtract the other C to the other side, making a new constant, and you're done, okay? So I got this. Now, to really solve this thing fully, if possible, we want to solve it for y, okay? So this negative y to the negative first, it's negative 1 over y. So how could I solve that for y then? All right, it's a good first step. Everybody okay with the fact that my plus c is still a plus c? Anybody upset that I didn't make it minus c? Good, because a constant is still a constant, whether it's positive or negative, doesn't matter. So still plus c, doesn't change. Okay, now what? Okay. So you want 1 over all of this jazz? Okay. Well, that's what I was just going to ask you. Can I pull the C out behind everything, or does it need to stay tucked under there like that? It has to stay under there. Mm-hmm. It's part of a denominator now, and you can't just pull a random number up out of a denominator and tack it on the end. So there it does have to stay there. Okay. So yeah, so that would be our equation then, or our solution to that differential equation that we started with. Okay. Now, if you can't solve it for y, it's okay. Just leave it the way it is. But if you're able to solve it for y, then usually that's what we do. Okay. Also, if they give you a point that it has to go through, then you could solve for that c, figure out what that constant has to be, and then you get a specific solution for one point. Doing it that way. So, how does this relate to exponential change and that sort of thing? Well, every exponential has the same differential equation. All of them are dy dx equals k times y, where k is a constant. So depending on the specific exponential that you're looking at, k could be lots of different stuff. But in general, their differential equations always end up looking like this. So why? Why is that always the case? Well, we can solve that question, or answer that question, by doing a little separation of variables here and solving this differential equation and seeing that it comes out into an exponential every single time. Okay? So if I separate my variables for this, dy dx equals k times y, how would I separate the variables? What do you think? What has to happen when you separate the variables? Why do we call it separation of variables? Right. Does it matter where the k goes? No. Put it whatever side you want, whatever's easier. Okay? It's just the x's have to be on one side and the y's have to be on the other side. So what do you think? How would I do that for this one then? Okay. Exactly. So what I would do is move the dx first, so then you can just slip the y underneath there. But it's going to end up looking like this. dy over y equals k times dx, right? We can do it that way. Multiply by a dx, divide by a y. And now we're ready to do our integration of both sides. Okay, so what is the antiderivative of 1 over y? Natural log. Natural log. Logs are related to exponentials somehow. That might come into play. Okay, oops, forgot my, I'm going to put the plus c on the other side. Okay, other side, what do I got? It's just a constant. What's its antiderivative? Nope. Kx. Going the other way, right? So you have to put an x there. And the k would still be there, right? Because if you take the derivative of kx, it's just k. And then don't forget we have this constant now that has to get tacked on there plus c. Okay, and then I want to solve this thing for y. If I have a natural log of y equals the other side, how do I solve for that then?
Don't you put like to that power?
Right, yeah. So y equals e to the kx plus c. Okay, now we can do a little playing around here with this thing because of some rules of exponents. So this is actually e to the kx times e to the c. You guys remember that rule of exponents? If you're adding things in an exponent, you can actually turn it into a multiplication problem with the same base then. Okay. Ultimately, if c is a constant, what's e to the c? Another constant, right? It's a number to a number. It's a constant. So we just give it another letter. Instead of writing e to the c, we just call it a. So this is actually a, and then I'm going to just shuffle it in front here instead, so it looks like this. I don't know. It doesn't have to be an a necessarily. You could make it a smiley face if you really wanted to, but well, the thing is, we don't want to confuse that constant with the other constant. So we got to call it something different. So we just use a different letter. Yeah. But anyway, so the solution to that differential equation looks like this, which is kind of your general form of an exponential, right? Some number times e raised to a number times x. So anytime we have an exponential equation, we're really just talking about that. Okay? So k affect what kind of exponential change we have. Okay, so look at the equation down there. When we talked about exponentials, we talked about the base of an exponential and how that affects whether it's a growth or decay, right? So what kind of bases, do you guys remember, make a growth, and what kind of bases make a decay? Do we remember from pre-calc? Yeah? Yep. So if we're looking at something that is we saw it like this. Well, it was a lowercase a, I guess, back then. But the ones you guys studied look like this. A times b to the x. And we said if b is greater than 1, then we have a growth. And if b was between 0 and 1, then it was a decay. Here is technically e to the k. Do you guys see that? That's really the base there. So how do we affect whether the base is going to be bigger than 1 or less than 1? What kind of a number could I put in for k and make that result come out smaller than 1? Negative. And what kind of k's could I put in there and make that result bigger than 1? Positive. So whether k is positive or negative affects whether it's a growth or a decay then, right? So if k is greater than 0, growth. And if k is less than 0, decay. Which should make some sense if you think about what a differential equation really is. A differential equation is measuring the change, right? So if a derivative is positive, the change is positive. It's increasing, right? We talked about that before. If a derivative is negative, the change is decreasing. It's going down, okay? So it would be a decay, all right? So that makes a bit of sense up here then, because dy dx, the derivative of this, is k times y. So if k ends up being positive, my derivative is positive. And if k is negative, my derivative is negative. So this determines then, right from that derivative even, whether or not we have a growth or a decay happening. Okay? And we're going to kind of use that to help analyze some stuff. Okay? So, let's see what we can do here. All right. So let's try something like this. So a substance has a decay derivative given by dy dx equals negative 0.0002 y. Determine its half-life. All right. And I do like what kind of what we're measuring as far as time is concerned. So it's going to be kind of a unitless answer, but we can at least do the half-life idea with this, okay? Now, sometimes with these, I wrote this as dy dx, but a lot of times you'll see it as dy dt because they're talking about time, okay? So just so you know, but you can still do this. So a couple different ways we could do this now. We could take this thing and do the separation of variables, kind of go the long way and figure it all out that way, or knowing where it's going to end up, because we just did that work, we could just pull this right into what its exponential equation needs to be with the k stuck in there and analyze that then. Okay? So that's going to be kind of the route I'm going to go with it since we already did all that work on the other page. So so that should be our exponential equation for it. Make sense? Just with decay stuck in there, right? What we came up with last time. So, how do I determine its half-life then? What does a half-life mean? The time it takes to do what? Decay, half of it gone, right? So, what's my initial amount of my substance in that formula? It's not an actual number, but what is it? A, right? That's where the initial amount is. So if this is my initial amount, this is the amount I have right now. So how could I use that to set up this thing to help me find a half-life? If I started with A, and I'm at the time it took to get to half, how much do I have right now?
Well, 2 for A and 1 for Y.
You could do that. I was going to say half A for Y, but yeah, same difference though, right? So I'm just going to do it this way because that's what I was thinking, but, right? You can do that too. Okay, I've got half as much as I had when I started, okay? Now, you look at this and you might think, okay, we're trying to the time, which is essentially X, but he's still got this A stuck in there. The equation, though, what are we going to be able to do with A now? I got an A on either side of the equation being multiplied. What can I do with that? Just divide them out, right? So they're gone. So it's 1/2 equals E to the negative 0.0002. That for X now. Okay? So step me through that process. What do I do? How do I solve that exponential equation? Okay. So natural log of 1/2. Don't forget the negative, though. All right, calculator time. What is the natural log of 1/2? So, anybody got that for me? Okay, do a little bit of division. Negative 0.693 divided by negative 0.0002. So what is my half-life? Should be a rather large number. Come on, guys. I know it's early. But what is it?
3,467. No, 65.7.
Okay. So, like, let's say we were measuring the time in years. Usually, that's what half-life is. So it would be like, 3,465.7 years for this thing to decay to half of where it started. Shortcut, because no matter what this number was, wouldn't I always end up with a 1/2 right here? If I have half-life, wouldn't this always be a 1/2? Has to be. Okay. Now, here's a little interesting fact. You guys remember your rules of logs? Does that little equation that I just wrote there make sense? The natural log of 1/2 is the same thing as the natural log of 2 to the negative 1. Bring down the negative 1, so it's actually negative natural log 2. Yeah? So I'm going to take this right here, and I'm going to generalize what we just did there for a second. Okay, so this is the same thing as that, right? So for these, negative natural log of 2 equals kx, right? My k in this case just happened to be that negative 0.0002. So I'm going to show you a little shortcut here. So can be found by using that equation. Because isn't that exactly what we did? We did the natural log of 1/2, which is the same thing as negative natural log 2, and we divided it by our k, which happened to be negative 0.0002. So this only works for half. You can do that. Okay? So it's kind of a nice little shortcut. If you know what the k, if you're given the differential equation that you're beginning with, or if you're even given the exponential and you can identify what the k is in the equation right there, then this is always going to work for you. Okay? So it's kind of a nice little way to go there where you can take care of it that way. So how then? So the half-life of fake element onium is 1,500 years. Come on, somebody has to laugh at that. That was supposed to be funny. No. Just a pity laugh, something. I mean, come on. So, route with this one. We're saying fake element onium has a half-life of 1,500 years. What is its differential equation? So can you take the backwards? All right, so start with this little equation right here that we just came up with. That's kind of our little shortcut into half-lives. So in this case represents the half-life, whatever it is, the time, right? So in this case, x is 1,500. Okay, so by using that little shortcut equation there, I can figure out the k, and if I know the k, I can just stick that into the differential equation, and I'm done. So it should be pretty quick. So k is going to be negative natural log of 2 divided by 1,500. So calculators, please. Don't take forever with it like you did the last one. What is negative natural log 2 divided by 1,500? Negative 4.6 times 10 to the negative 4. Okay. And with that, as long as it's not too crazy long, we can go ahead and put that into decimal form because usually we see them written that way instead. So it'd be negative 0.1234. Yeah, 1, 2, 3, 4. That should work. Okay, so it's negative 0.00046. Okay, so if that's k, remember our differential equation that we talked about all the way at the beginning. That's right. dy dx is always k times y. Well, I know my k now, so I got it. As long as it's an exponential decay, which half-lives always describe exponential decay. So I can rewrite my differential equation. Dy dx equals negative 0.00046 y. So I can come back to it that way. Make sense? As long as you know your k, you know your differential equation. So you can do it like that. What else can we do? So if you guys are going to be doing with exponentials here, it's going to be a lot of review from pre-calc, and you don't necessarily need the calculus to do it. As far as involves some sort of differential equation. But they might have some general questions about exponentials. So like, what's the formula for an exponential equation that goes through a couple of points or something like that? So let's say an exponential function passes through the points 0, 4 and 2, 9. Oh, come on, seriously?
You're writing too aggressively.
I know, I must be. Just give you a couple of points that it passes through. What's the equation of that exponential curve? Okay, so let's go back to our kind of generic equation here. So every exponential is going to look like that. Some form of y equals a to the times e to the kx. And if I have an equation for this curve, I need to solve for two things. I need to figure out a, and I need to figure out k. If I know those two numbers, my equation is done. All right? So one of those two is kind of staring me in the face already from the problem. Which one of those two, a or k, do I already know? Yes. What is a? Rachel, do you know what it is? No? Oh, good guess then. It's 4. Right. Now think about this. A is the initial value, right? It is the value of y when x is 0. Right? So what is the value of y when x is 0? 4. Right? Because I gave you the point 0, 4. I made it 0, 4 on purpose. So, and even remember that fact, you can even just plug it in and say, okay, so 4 equals a times e 0, right? Because fx is 0, this is all zeroed out. But e to the 0, 1, right? So that means a equals 4. So I can take that then, and now I have y equals 4e to the kx. And then I got this other point. Well, what do you suppose I'm going to do with that other point? Plug it in and see what I get for k. So if I go 9 equals 4e to the k times 5, divide by 4, so I got 9/4. Huh? Oh, yep, it's 2. You're right. Thank you. 9/4 equals e, and we'll just say 2k. So again, what do I do now? Right, yeah, the natural log of 9/4 equals 2k. So, natural log of 9/4, whatever you get from that, divide that thing by 2. I should have it. Yeah, so k is equal to 0. We'll say 405. So then my exponential equation, y equals 4e to the negative, to the 0.405. Is this an exponential growth or decay? Growth. How do you know it's a growth? You got it. K is positive. You know it's growth. Okay. So there are going to be some other questions similar to this, like I said, that are going to kind of hark back to some just doing regular exponential style questions. And there's some reading I want you guys to do as well with this. I always put reading in the assignments, but sometimes I wonder if people actually do it. So this one I'm really going to encourage you to read a little bit. It's going to be a review of some things from pre-calc. The formulas of, like the formulas, Newton's law of cooling, that sort of thing. They got some other good examples in here that I want you to take a look at, okay? That, I think you guys are kind of good, pretty much good to go here with the basics of what I wanted you to understand this stuff. So I'll let you guys have some time to work.